morning, dear students. Today my aim is to give you a quick view of the differential equation, the solution of all types of differential equation, especially for the graduate students, BSc non-medical, BA students with mathematics, BSc CSM, and all those graduation classes in which you are having mathematics as a subject and differential equations as a topic. My aim is not to go to the detail, to concepts, to the theory, but the aim is to give you the methods how to solve various types of differential equations. Right from the starting, there is the differential equation of first degree and first order, and to the solution in series. I'll take up these all methods in 4 to 5 videos. So it is the first video where we are going to start with the differential equations of first order and first degree. You can take this lecture as a revision class of solution of differential equations. So the first type of differential equations is the differential equations of first degree and first order. The first method of solving a differential equation is the simplest equation, that is the variable separable form. When a differential equation is in variable separable form, we can solve it very easily, as it is clear from the name variable separable. In such types of differential equations, we can separate the variables in left hand side and right hand side, and then by simply integrating we can get the solution. So a very easy question, a very easy example I am going to take here. For every method I will illustrate it with a simple example. Here the example is y minus x dy by dx is equal to a y square plus dy by dx. This differential equation is one of the examples that can be solved by using the variable separable method. What we have to do: collect all the terms containing dy by dx on one side and rest of the terms on the other side. So this term is containing dy by dx and this term is containing dy by dx. Collecting these two terms, we can get a plus x dy by dx. I have taken this term to the right hand side. Now the rest of the two terms are this y and ay square. Since this term has gone to right hand side, ay square will come onto the left hand side, giving us y 1 minus ay. Now all the y's can be collected on the left hand side by taking this to the denominator, and taking dx and a plus x to the right hand side, we can separate the variables in this equation. And what we will get? We will get dy over y 1 minus ay is equal to dx upon a plus x. Now variables are separated and our next aim is to integrate both sides. Integrating both sides, what we are going to get? Here, by our previous methods, by approach to knowledge, we know that this can be integrated by using partial fractions. For partial fractions, what I am going to do, I am taking two factors in the denominator separately, y, in the other I am taking in the denominator 1 minus ay. Considering y as 0 and putting the value of y is equal to 0 in the rest of places where y is here, in the numerator we are having 1, in the denominator we are having 1 minus ay, that means 1 minus a into 0. Similarly, when we are considering this factor, if we take 1 minus ay equal to 0, we will get value of y is equal to 1 upon a, and substituting this value of y everywhere in this fraction, leaving this 1 minus ay intact, will get 1 in the numerator, and this y will become 1 upon a. On the right hand side, we are having dx upon x plus a. This will be easily written in the form 1 upon y and plus a upon 1 minus ay dy is equal to integral dx upon x plus a. Now integration is very easy. This 1 upon y is log of y. This is a, it is a constant, can be taken outside, and integral of 1 upon 1 minus ay is log of 1 minus ay divided by minus a. On the right hand side, integral of dx upon x plus a is log x plus a plus some constant of integration. Since all the terms are in log, we can take the constant of integration also as log c. Now it is a is cancelled here, so left hand side is log of y upon 1 minus ay. On the right hand side, it is log of c x plus a. Taking exponential both sides, y upon 1 minus ay is equal to c x plus a, and it is the required solution of this given differential equation by using variable separable method. Next is the method when the equation is not directly solvable by variable separable method, but it can be converted into variable separable form. Such a differential equation, we will name it as reducible to variable separable form. That means the equation is not at first sight is variable separable, but we can convert it into the variable separable form. Let us take, especially I am telling you that such an equation will be of the type dy by dx is equal to f of ax plus by plus c. Such an equation will be of variable separable form. Let us consider some example. So here I am taking the example dy by dx is equal to 4x plus y plus 1 whole square. This equation, this is not in variable separable form, but can be converted. How? We substitute this 4x plus y plus 1 is equal to z. Now differentiating both sides with respect to x, what we will get? We will get 4 plus dy by dx is equal to dz by dx. Now substituting these two values, 4x plus y plus 1 is equal to z, and 4 plus dy by dx is equal to dz by dx in this equation, that is equation number 1, what we will get? This dy by dx will become dz by dx minus 4 is equal to, this term will become z square. And now take this minus 4 to the other side, you will get dz by dx is equal to z square by 4 plus 4. Clearly, now it is in the variable separable form. We can take all z to the left hand side and dx to the right hand side. We will get dz over z square plus 2 square is equal to dx. Now the next aim is to integrate. Integrating it, this is dx upon x square plus a square, whose the formula for integration is 1 upon a tan inverse x upon a. It will become 1 upon 2 tan inverse z by 2 is equal to integral of dx is x plus c. Take this 2 onto the right hand side and take tan on both sides. you will get z by 2 is equal to tan of 2 times x plus c. And this 2 can also be taken on the right hand side, and substituting the value of z to be 4x plus y plus 1, we will get 4x plus y plus 1 is 2 times tan 2 times x plus c, which is the required solution of this equation, which was not directly in the variable separable form, but we reduced it to variable separable form and then solved it. Next is the method that is used to solve the homogeneous equation. Let us first discuss what a homogeneous differential equation of first degree and first order. A differential equation which is of the type dy by dx is equal to x power n and then some function of y upon x. Such an equation is called a homogeneous differential equation of first degree and first order of degree n. Now, here degree n means the x raised to the power n. This n we are taking as the degree of the homogeneous function, not of the differential equation. It is the degree of the homogeneous part of the differential equation. Such an equation we solve by substituting y is equal to vx, which in turn give dy by dx is equal to v plus x dv by dx, and then we will use these two to solve the differential equation given in this form. So, one of the example, an illustration, we can take it as, consider this differential equation, x square plus y square dx minus 2xy dy is equal to 0. Consider this differential equation. In this differential equation, if we take this term 2xy dy to the right hand side, we will get here this 0 will be eliminated and this will become in this form equal to 2xy dy. Now take dx to the side and 2xy in the denominator on the left hand side, it will become dy by dx is equal to x square plus y square over 2xy. Now this is a homogeneous differential equation because the degree of each term in the numerator is equal and there is only one term in the denominator. As I have discussed, we will substitute y is equal to vx. Putting y is equal to vx and from it obtaining dy by dx is equal to v plus x dv by dx, if we use these substitutions here in the equation, this dy by dx will be v plus x dv by dx, v plus x dv by dx is equal to, on the other side, wherever there is a y, we will put y is equal to vx and we will get x square plus v square x square upon 2x into vx. X square can be taken out from the numerator and x square is there also in the denominator, can be cancelled out. So the right hand side will take the form 1 plus v square upon 2v. So v plus x dv by dx is equal to this now. This v, we will take it to the right hand side so that x dv by dx is equal to 1 plus v square upon 2v minus v, and this can easily be solved into the form 1 minus v square upon 2v by taking 2v as LCM. It is now clear that all the v's can be collected to the left hand side and 2x dx and x can be taken to the right hand side, so that we will get 2v upon 1 minus v square dv is equal to dx by x. Integrating both sides, what we are going to get, on the left hand side, if we take this 1 minus v square, if we substitute it as t, minus 2v dv will become dt. But if we are introducing a minus sign here, we will have to put a minus sign also on the right hand side. Now this is your t and this portion will be dt. So this is dt upon t, that means log t. So you will get log t is equal to minus log x, and once again, since both the terms are in log, we will take the constant of integration also as log c, which gives log of t is equal to log of c upon x. Taking exponential to the both sides, we will get t is equal to c upon x. This means x t is equal to c, and substituting the value of t was here 1 minus v square. So we will get x 1 minus v square is equal to c. Still, v is a variable which was not there in the original differential equation, so we will have to put the value of v also, and the value of v you can have from here. V is y upon x. Putting v is equal to y upon x here, what you are going to get, this equation will take the form x square minus y square is equal to cx, which will be the final solution of this differential equation. As in the first case, we saw that some equations were not in the variable separable form, but these equations can be reduced. Similarly, there are some differential equations which are not in the homogeneous form but can be reduced. Such equations are especially of this type: dy by dx is equal to a1x plus b1y plus c1 upon a2x plus b2y plus c2, with a1 upon b1 not equal to a2 upon b2. The question is, why this condition? Because if this condition is not there, that means if a1 upon b1 is equal to a2 upon b2, we will get the same factor of x and y in the numerator and denominator, and substituting that particular factor equal to z or t, this equation will be reduced to the variable separable form, and we will be solving it by the previous one method. Putting this condition, this cannot be solved by variable separable method directly, cannot be reduced into that form, and we will reduce this equation then to the homogeneous form, and then we will solve it. So let's consider an example once again. Suppose we are getting this question dy by dx is equal to 2x plus y plus 1 upon x plus 3y minus 5. Now in this equation, a1 upon b1, that means 2 upon 1, is not equal to a2 upon b2, that means 1 upon 3. So this equation can be reduced to the homogeneous form. How? We will substitute small x to be capital X plus h, and small y is equal to capital Y plus k, so that our d small x will become d capital X and d small y will become d capital Y, and the given differential equation will take the form d capital Y upon d capital X is equal to, the first term 2 small x will be 2 capital X plus 2h, the second term plus y will become plus capital Y plus k, and this constant term plus 1. Similarly, the denominator, this x will become capital X plus h, this 3y will become 3 capital Y plus 3k, and the constant term minus 5. What we will do now? Now we will take these two brackets to be equal to 0, because if these two are equal to 0, rest of the equation will be only this type. dy by dx is equal to 2x plus y over x plus 3y, and this is clearly a equation in a homogeneous form and can be solved by using y is equal to vx. So we will take this 2h plus k plus 1 is equal to 0. We will take h plus 3k minus 5 is equal to 0. Solving these two equations, that means you can say multiplying this equation by 2 and subtracting h will be cancelled, minus 5k and plus 11 is equal to 0, giving k is equal to 11 upon 5. Similarly, if we multiply the first equation by 3 and subtract again, we will get 5h plus 8 is equal to 0, giving h is equal to minus 8 upon 5. That means our small x is equal to capital X plus h, that means minus 8 upon 5. Similarly, small y is capital Y plus k, k means plus 11 upon 5. Now, if we substitute these values of x and y in this equation, automatically the last two terms here, these will be removed as these will become 0. For the rest of equation, we know that what we have to do, put y is equal to vx, so that this dy by dx will be v plus x dv by dx is equal to 2x plus vx over x plus 3vx. X will be taken out and can be cancelled. It will become 2 plus v upon 1 plus 3v. Taking this v to the other side, x dv by dx is equal to 2 plus v over 1 plus 3v minus v. Taking 1 plus 3v LCM, we will get 2 plus v minus 3v square. This v is cancelled out. You will get x dv by dx is equal to 2 minus 3v square over 1 plus 3v. And now clearly this form is in the variable separable. These two terms can be taken to the left hand side, x and dx can be taken to the right hand side, and then it can be solved by using the method used in the variable separable form. So I'm not going into the detail, you can solve it because now only simple integration remains. But when you will get the solution, you will get capital V, you will get capital X, you will get capital Y. You will have to substitute the values once again. Capital X is equal to small x plus 8 by 5. Capital Y is equal to small y minus 11 by 5 to get the final solution in small x and small y. Next is the method to solve linear differential equation. What a linear differential equation is: any differential equation of the type dy by dx plus py is equal to q, where p and q are the functions of x only, is a linear differential equation. And how to solve it? Multiply both sides of this equation by e raised to the power integral of p dx. This is called integrating factor. I am writing here integrating factor. So multiplying both sides by e raised to the power integral p dx, what you will get? You will get e raised to the power integral p dx into dy by dx plus y into p e raised to the power integral p dx is equal to q into integral e raised to the power p dx. You will get this now. Look at it carefully. What you are getting here, this is e raised to the power integral p dx into derivative of y plus y into derivative of e raised to the power integral p dx. That means u into derivative of v plus v into derivative of u, that means the derivative of the product uv. So what the left hand side is, it is actually derivative of y into e raised to the power
integral p dx. On the other side, you will get q into e raised to the power integral p dx as it was earlier. Taking dx to the other side and integrating, what you are going to get? You will get y into this e raised to the power integral p dx, which is if. So y into if is equal to q into this q multiplied by if and the dx coming from here and then integration. So this will be the solution, plus you can write the constant of integration. So this will be the solution. Whenever a linear differential equation is there, dy by dx plus py is equal to q, the solution will be y into if is equal to integral q into if dx plus c. So we'll take a simple example once again to illustrate this method of solving differential equation. So consider this differential equation: x square plus 1 dy by dx plus 2xy is equal to 4x cube. Consider this differential equation. If we multiply both sides by 1 upon x square plus 1, this equation will take the form dy by dx plus 2x upon x square plus 1 y is equal to 4x cube upon x square plus 1. So it is dy by dx plus, this is your p, dy by dx plus py is equal to q, and clearly p and q are the functions of x only. So this is a differential equation which is linear. What will be the if now? The if is e raised to the power integral p dx. That means e raised to the power integral p is this 2x upon x square plus 1 dx is equal to, if you put this x square plus 1 as t, if you put this x square plus 1 as t, this 2x dx will become dt. So this is integral dt upon t, and integral dt upon t is log t. So this will become e raised to the power log of x square plus 1. That means x square plus 1. This is your if. Therefore, solution of given differential equation is y multiplied by if. If is here x square plus 1. So y into if is equal to integral q. Q is this 4x cube upon x square plus 1 multiplied by integrating factor if, this is x square plus 1, and then dx. This x square plus 1 will be cancelled and the constant of integration. What you will get, y into x square plus 1 is equal to 4x cube dx, that means x raised to the power 4 plus c, which is the solution of this differential equation. As in the two previous cases, we have seen that some of the equations are not directly in the variable separable form but can be reduced. Some of the differential equations are not in the homogeneous form but can be reduced. Similarly, some of the differential equations are not directly linear differential equations but can be reduced to the linear differential equation form. One such form of differential equations is Bernoulli's form of differential equation. Bernoulli's form of differential equation is dy by dx plus py is equal to q into y raised to the power n. How to solve it? Just multiply both sides by 1 upon y raised to the power n. You will get y power minus n dy by dx plus p, this y multiplied by this is y raised to the power 1 minus n is equal to q. Now, if we substitute y raised to the power 1 minus n as z, 1 minus n y raised to the power minus n dy by dx will become dz by dx. So this y raised to the power minus n dy by dx will become dz by dx into reciprocal of 1 minus n. So this will become 1 upon 1 minus n into dz by dx, this term, plus p into y raised to the power 1 minus n. This y raised to the power 1 minus n is z, is equal to q. Multiply throughout by 1 minus n, and the equation is now dz by dx plus p dash z is equal to q dash, where p dash is 1 minus n into p and q dash is equal to 1 minus n into q are both functions of x, and since the equation is now linear differential equation, can be solved by the previous method. That means the solution will be y into integrating factor is equal to integral of q into integrating factor dx plus the constant of integration. So once again we will take up some examples to illustrate this method. So consider this equation, dy by dx plus 2y tan x is equal to y square tan square x. Look at this equation. This equation is not in the linear differential equation form, but if we multiply this equation by 1 upon y square, what we will get? Y power minus 2 dy by dx plus 2, here this y upon y square will be y power minus 1 tan x is equal to tan square x. Taking this y raised to the power n 1 minus 1 as z, we will get minus y raised to the power minus 2 dy by dx is equal to dz by dx, and this y power minus 2 dy by dx, this term will become minus dz by dx. So minus dz by dx plus 2, this is your z, tan x is equal to tan square x. Multiply throughout by minus sign, this minus sign will be removed from here, it will become negative sign here, and you will get a minus sign here too. This equation is now dz by dx plus pz is equal to q. What is your p now? Your p is minus 2 tan x and your q is minus tan square x. What will be the integrating factor? Integrating factor is e raised to the power integral minus 2 tan x dx. That means e raised to the power minus 2, and integral of tan x is log of cos x. That means e raised to the power log of cos raised to the power minus 2x. Since e raised to the power log k is k, so it will become secant square x. This is your IF. So what will be the solution? Solution will be z, because the equation is in the variable z and x. So z into if. If is secant square x is equal to integral of q. Q is minus tan square x multiplied by if. That means secant square x dx. Now take this tan x as t. This secant square x dx will become dt. So what you will get? Integral minus t square dt, and minus t square dt means minus t cube by 3. So you will get z secant square x is minus tan cube x by 3 plus the constant of integration. And now substitute the value of z. Z was y inverse, that means 1 upon y. So you can put secant square x upon y is equal to minus 10 cube x upon 3 plus c is the solution of this Bernoulli's form of linear differential equation. Then we will move on to the exact differential equation. Now exact differential equation, when a differential equation is exact, suppose we write some differential equation in the form m dx plus n dy is equal to 0, where m and n are both functions of x and y. If curly m by curly y, that means the partial derivative of m with respect to y is equal to partial derivative of n with respect to x, then we say that this differential equation is in the exact form and its solution is integral of m dx treating y as a constant, plus integral of terms of n not containing x and their integration with respect to y is equal to the constant of integration will be the solution of an exact differential equation if this curly m by curly y is equal to curly n by curly x. We can take some example to illustrate it. Suppose we take this question x square minus 4xy minus 2y square and then dx plus y square minus 4xy minus 2x square dy is equal to 0. Look at this differential equation. Here m is x square minus 4xy minus 2y square and n is y square minus 4xy minus 2x square. What is curly m by curly y? Curly m by curly y, 0. Here you will get minus 4x, here you will get minus 4y. And what is curly n by curly x? Here it is 0, here it is minus 4y and here it is minus 4x. So the value of curly m by curly y is same as the value of curly n by curly x. That means this differential equation is exact. And once the differential equation is exact, we know that this will be the solution. So what will be the solution? The solution is integral of m dx. So here is your m, that means x square minus 4xy minus 2y square dx, treating y as a constant. Plus integral terms of n not containing x. So here it is n and only one term is there, y square, which does not contain x. Here there is x, here there is x, so this is the only term that does not contain x. So we will have y square dy is equal to c, the constant of integration. Now here we have to integrate treating y as a constant. So what will be the integral of x square? This is x cube by 3 minus 4y is a constant and integration of x is x square by 2 minus 2y square is a constant and 1 dx is x plus y square dy is y cube by 3 is equal to the constant of integration. Simplifying, we will get the solution. So this is the way how to solve a differential equation which is exact. Suppose a differential equation is not exact, then there are methods to convert it into the exact form
by multiplying by some integrating factor. How to find integrating factor is a big question now. So there are two methods. One is the method of inspection, and there are 5 rules also to find integrating factor if it is not directly visible. First of all, if the differential equation contains two particular terms, then by inspection we can have the integrating factor. Suppose your differential equation contains x dy minus y dx. Suppose your differential equation contains this term and some more terms. Then, looking at some other terms, we can have integrating factor by inspection. In some of the cases, integrating factor will be 1 upon x squared. Why? Because if we multiply by 1 upon x squared, this term will become x dy minus y dx upon x squared, which is equal to d of y by x. You can check x dy minus y dx over x squared. So looking at the other terms, if suitably multiplying by 1 upon x squared, the other terms are also simplified. We will take integrating factor as 1 upon x squared. If not, the second case, some of the times 1 upon x squared will not work. We will use then the integrating factor as 1 upon y square, because if we multiply by 1 by y square, what it will become? It will become d of minus x upon y, which will solve our purpose if the rest of the terms are also doing well with 1 upon y square. If not, again we have 1 upon x square plus y square as a term, because if we multiply by 1 upon x square plus y square, it will take the form of d of some terms tan inverse, maybe y upon x, maybe x upon y, or something like that. Even some more integrating factors in this case are possible. On the other hand, suppose your differential equation is containing x dy plus y dx. Then you can have 1 upon xy as the integrating factor, because it will again convert it into d of something. Even x square plus y square will convert into the perfect differential form d of something. So these are the integrating factors by inspection, but will be used in view of the rest of the terms. Other than this particular term, if the rest of the terms are doing well with these integrating factor, we will use the integrating factor accordingly. If not, that means if x dy plus y dx or x dy minus y dx is not there, then there are 5 rules how to get the differential equation into the exact form, and that we will cover in our next lecture. So I think you are doing well with these methods. Next methods, that is how to convert a differential equation not containing x dy plus y dx or x dy minus y dx into the exact differential equation. There are 5 rules which we will discuss later on. I think you like this video, and if you like this video, I hope you like, share and subscribe this YouTube channel to continuing your study with this YouTube channel on differential equation, on topology, on complex analysis, on algebra, on several motivational lectures, as well as some poems. Thank you.